Hello everyone, welcome back to another video. Today I want to talk about a project that I completed as part of a summer camp in artificial intelligence. This is a summer camp that I did a while ago, but I learned a lot about artificial intelligence and it really helped me dip my toes into this new technology that I wanted to share what I learned in this camp and also show the final product, which I think I'm pretty proud of. So hope you enjoy, and I'll try to explain it as best as I can.
Hello, my name is Akshay Kumar. Today I'll be talking about teaching cars how to drive with deep Q learning for self-driving cars. Machine learning for self-driving cars. Self-driving cars are basically autonomous cars that use advanced AIs to operate on the road without any human input. And in this project, I created a self-driving car in a closed environment that would operate on its own in a racetrack. Why do we need self-driving cars? More than 38,000 people die every year in crashes on US roadways, and the average American spends 18 days a year behind a wheel. Self-driving cars have advanced AIs, and with the help of these, we can reduce the risk of something like driving, and it can also free up time spent behind a wheel. So, how will the car drive? As you can see in the image on the right, this will basically be your environment, a racetrack and a car. We'll use reinforcement learning for decision making on whether the car should move forward, left, right, or brake, and computer vision to observe the car's surroundings. So, what is reinforcement learning? Reinforcement learning is basically the act of having actions and rewards for each state. The agent, in this case the car, will have an action, be it forward, left, right, on the environment, the racetrack, and that will produce a state and a reward. The state will be what we desire, what it looks, what it sees, and what it acts. And the reward will be what the computer gets as feedback, whether it did well or wrong. And so, with the help of this and running it constantly again and again, we can help train the agent to perform the best action for its environment and provide the best state and get the best reward. First, we use policies in reinforcement learning. Policies are basically actions given the state. They function as rules and guidelines. Our first policy was to read the road using pixel intensity. As you can see in the middle, this is what the car would basically, or the model would basically see. And then we made policy that punishes staying still and punishing getting off the road. As you can see here, this is our reinforcement learning using just policies and a few punishments. As you can see, it just went straight and curved off road. It didn't know what to do. So we can do much better. Our first strategy was to implement behavioral cloning. We basically fed the model approximately 20 minutes of a human driving around the racetrack so that the model could observe and see what decisions it made to be able to replicate and implement that. And combining with our reinforcement learning and our behavioral cloning, we got an accuracy of about 87.4%, which looks pretty good. However, when you see how our model did with our behavior cloning and our policies, you can see that didn't perform as good as expected, or that we could do better. And the reason because is the moment the car got off road completely, it had no clue what to do, because both our behavioral cloning and our policies did not instruct the car on what to do once it got off the road. It only punished it for going off the road. So we used something called Q learning, which is an iteration of reinforcement learning that is much more robust and works better over larger periods of time. A Q learning basically applies a specific quality for every action and state, and a Q function will return the best possible reward. And we will run the simulation again and again, and it will generate a table for each state, each action, and a quality given for that. And the reason why this is more robust and better is because of the equation in the bottom, the Bellman curve, which helps it estimate future rewards given past rewards, basically helping the model teach itself better than a reinforcement learning could. However, this won't suffice because while it does create a Q table, it wouldn't work for driving because there's almost an infinite amount of states and almost an infinite amount of actions. And so the Q table would be infinitely long or unfeasible to calculate. So we would use something called deep Q learning, in which uses Q learning with a neural network to approximate Q values instead of putting them in a table. and this will allow you to input any state, and it will be able to calculate the value or the reward for that state instead of referring back to a table. And this is the best for our model, and this is what we ended up using. Next, we have a problem of exploration versus exploitation. Usually the model will perform the best action given the state. However, in the training phase, to get the best reward, we'd have to experiment a little. And this is where exploitation and exploration comes from. Exploitation is performing the best action given the state. And that's what we want to do most of the time. However, for every action, there will be a chance that the agent will perform a random action that is completely unsupervised, just a random action. And this will be the exploration, in which it will just do something new that the model hasn't done yet to be able to read and understand the value and the reward for it. And this will basically allow the model to hone in. And a good analogy would be in an arcade or a casino. You'd want to spend some time on the machine that is the best or pays out the most, but you also want to spend some time exploring other machines. And that's basically how our model would be able to hone in on the best actions. So here's our demo of deep Q learning. As you can see, just from this, it's much better from both our reinforcement learning and our Q behavioral learning. It seems much better, and because of all this iteration and processing power, it was able to stay completely on the road at almost all time. So, moving forward, our testing environment wasn't an accurate depiction of real-life roads. As you can see, it didn't include other cars, traffic, or obstacles. It just had a racetrack. And so, if we wanted a more robust one in the real world, we'd need more advanced computer vision that had cameras and sensors instead of just reading RGB values. And we'd also have more advanced decision making alongside a lot more training, a lot more testing, instead of around 20 minutes of behavior cloning and a few epochs of deep Q learning training. Thank you for listening.
Thank you for listening. I hope you enjoyed the presentation, and I hope you learned as much as I did when I first started off doing this project. I learned a lot, and I wanted to share some of that with you guys. If you have any questions, please leave them down in the comments, and I'll try to answer them as much as I can. And once again, thank you for listening.